Welcome back to INST 314, Statistics for Information Science, with your host, Shawn Janzen. We're continuing our topic on one-sample Z and T hypothesis tests, and we're continuing this topic module into critical regions. We've talked about critical regions a little bit before, but we're going to expand on it with a deeper treatment here as it pertains to the Z and T hypothesis testing. So let's recall that critical regions are the area under the sampling distribution that includes unlikely sample outcomes. What do we mean by unlikely? Well, this is where we're talking about alpha. Alpha, we said before, is the maximum amount of risk that you are willing to take in your analysis. And so we set this before we start the analysis. And any value we have, if we have a p-value less than our alpha, we're statistically significant, meaning that probability is unlikely to have occurred by chance alone if the null hypothesis distribution is true. Now, we're not going to talk specifically about p-values, so we're going to flip gears to critical values. And critical values for Z's and T's are the Z or T score that's associated with a given level of alpha. And this level of alpha, the Z or T score critical value is going to differ depending if we have a one-tail or a two-tail test. And that we're going to be comparing it against the Z or T obtained. This is the Z or T score we get from doing our hypothesis test. This is an analogous to where we talked about before with the chi-squares, where a chi-square had a critical value that was found at some given level of alpha of interest and a degree of freedom. And then we had a chi-square we obtained from doing the chi-square analysis. If our chi-square obtained was larger than our critical value, we were statistically significant and could reject the null hypothesis. The same idea applies here, that we are going to get a Z or T score obtained. We are going to compare it against a Z or T critical value that we are going to find based at some level of alpha, and if it is larger, we will be statistically significant and can reject the null hypothesis. Now, let's go ahead and show you a few different versions here, how this could differ with an alpha of 0.05. I have three different normal distributions up on the screen here. And in the upper right, we have a two-tail normal distribution. In the lower left, we have a one-tail lower, and then in the lower right, we have a one-tail upper. In the two-tail version up top, our alpha 0.05 is split under two halves. We have to go into the two different tails. And so I've shaded in there where we have probabilities of 0.025 on both sides of the curve. And what we're going to find as we look up our Z critical values is that a two-tail alpha 0.05, where we have to look on both ends of the curve, is going to give us a critical value at negative 1.96 on the left and positive 1.96 on the right. When we look down to the lower distributions, lower and upper respectively, we have all of that 0.05 packed into that particular tail, the left or the right. And when we do that, that red shaded region pushes out farther than it would have if it wasn't split up into the two halves. And if we look up a probability of 0.05 for a one tail, that's going to give us a lower tail version of negative 1.56 and a positive version of positive 1.96. So the takeaway on this particular slide here is that at any same given level of alpha, the critical regions are going to be larger in the one tail and smaller in the two tail. We've talked about this in previous videos, but I just wanted to come back to this idea. But let's go ahead and look up how these critical values change based if we're looking at a one tail or two tail. So in this slide here, I have a screenshot of a Z table, and I've got colors bars in green and red. The green is going to help us find our one tail critical value, and the red is going to help us find the two tail. So you start working backwards on a Z table, look at the probabilities, find the probability you're looking for, and then find out what Z value it corresponds to. So if we're looking for a probability of 0.05, this is going to go ahead and start in the upper left and work our way down to the lower right, looking for the 0.05. This is the probability that's going to have that all packed in the lower left tail region. And as we look down, we're going to find our way to a probability of 0.0495. That's the closest we're going to get to 0.05. You might say that the 0.505 is also equally close, and you wouldn't be wrong. If this table had extended decimals beyond this, we would find that our closest value is at the 0.0495. And so if we back this out, we can find that it is associated with a z-score of negative 1.65. Now, the z-table is symmetrical, so if we were to look for a probability of 0.95, which is the probability we would look for finding a positive tail test there, then we would find that's located at a z-score of positive 1.65. Now, if we switch gears into the two-tail version, we said that we have to split alpha into two halves. So we're going to be looking at the lower and upper tails where that 0.05 is cut in half. So we're going to find the probability of 0.025. And that actually falls exactly where it corresponds to a z-score of negative 1.96. And if we were to have the positive side, we'd look at probability of 0.975, and that is going to land at positive 1.96. And this is where we go ahead and get our z-scores associated of the one-tail and two-tail at an alpha of 0.05. Let's put this in reference now to how we find the t-critical value, which is very similar, but we read the t-table differently. In z-scores, we do not have degrees of freedom, but in t-scores, we do. So what we have on a t-table is along the column on the left, we have the degrees of freedom, and up top, we indicate how many tails we have. Now, in the version I give you for class, I give you at top, there's a difference between the one-tail and the two-tail. But if you're just on the internet hanging out and you find some that do not differentiate between them and it only has one alpha level up top, keep in mind you're going to have to use the alpha level based on the amount that's listed under that curve. So if we were doing an alpha of 0.05 and it didn't mention the difference between one-tail or two-tail up top, you'd have to look, you may have to differentiate into a 0.025 alpha level up top. But keep in mind, that's only when you have t-tables that don't differentiate between one-tail and two-tail. On this one, in this example, I have. So again, the green bars are going to help us find the one-tail version, and the red bars are going to help us find the two-tail version. So up top, we've gone and located at the green row on the one-tail, where our alpha says 0.05. And in this case, for the example, we're looking with 25 degrees of freedom. And you bring that down to where we have 25 degrees of freedom, and we get a lower tail value of 1.708. Now this t-table is in absolute value terms, so if you're doing a lower tail test, just make this a negative 1.708. If you're doing an upper one-tail test, we're going to have a positive 1.708. Let's switch gears to if we're doing a two-tail version. Two-tail version, we're going to find where alpha is 0.05, and I'm going to go down to where we have the degrees of freedom equal to 25, and it intersects at 2.060. Now again, I said this is in absolute terms, so that means it's at a negative 2.06 and a positive 2.06. On this next slide here, I'm giving you some tables just to kind of help give you frames of reference for some commonly used alpha levels and how it affects the z-criticals. In the table up top, I'm showing you how the critical value is going to change based on if we're doing a two-tailed test, which is the not equal sign, or a one-tailed test with the greater than or less than symbols. And note here how we had just shown that with the z-critical, we have the plus or minus 1.96 for the two-tail and the positive and negative, respectively, 165 for the upper and lower tails. If we have the t-critical, I just have, in this case, 10 degrees of freedom, and you can see how the two-tail is plus and minus 2.228, and the one-tail is plus 1.812 and negative 1.812 for the upper and lower tail, respectively. Note how these scores are larger than their z-critical values. This is because t is working to approximate z as n becomes large, so it's going to be larger than its z-critical value counterparts, but as the sample size becomes larger, so too shall our degrees of freedom, and those critical values for t are going to become closer and closer to their z counterparts. The table off to the side here, this is where I can show you how do the critical scores for z and t change as we look at, this one is just z-scores, but how do these critical scores change as our levels of alpha change for the two-tail and one-tail? So we start at alpha at 0.1, and we get a two-tail of plus or minus 1.65, upper and lower tails at plus and minus 1.29. As we get to 0.5, two-tail goes to plus or minus 1.96, upper and lower tails go to plus and minus 1.65. And as we work our way down the table, what we will find, and the pattern holds, that as alpha decreases, the critical values, regardless of if it's two-tail or one-tail, the critical value is going to become larger. Think of this graphically. You are decreasing that red shaded region of the critical value. As you make alpha smaller, that red shaded region becomes smaller. It becomes harder to get a score into those red shaded regions. The critical value that's associated with those lower alpha scores is becoming larger. It is a number farther away from the center of that distribution where it starts at 0. So as that red shaded region becomes smaller, the two-tail or one-tail values are both becoming larger as well. That's your takeaway on this. Now again, I just want to reiterate, I mentioned this in a previous lecture area, that there's an inherent tension between a type 1 and type 2 error. Type 1, just reflect, this is our alpha error. This is what's going to happen if you reject a null hypothesis that's actually true. And a type 2 error is our beta error, where we fail to reject a null hypothesis that is actually false. Now, as we go ahead and make our type 1 errors smaller, we are reducing the chance of the type 1 error, but we're going to increase our chance of the type 2. So keep in mind that the lower your alpha, the larger the non-critical area, the higher the probability to obtain a value that's in that non-critical region. So that's the long-winded way of saying higher chance of a type 1 error. You're never going to be able to avoid both type 1 and type 2. It's a trade-off that you're going to have to figure out based on the context and the importance of whatever it is you're studying. Which one is more important of having, the type 1 or the type 2 that you need to mitigate? Now let's just briefly talk about T confidence intervals. In the previous videos, we talked about Z confidence intervals. And if you can do a Z confidence interval, you can totally do a T confidence interval. The formula for it is almost exactly the same. You start with some X bar, the mean of your sample, plus or minus some margin of error. That margin of error in a Z-score is Z times standard deviation, which is divided by the square root of n. In this case, we're taking out Z and we're plugging in T. Now the T is the critical value that is based on its degrees of freedom at a given level of alpha. So the T critical score is going to change based on the degrees of freedom in the critical alpha. It's also multiplied by standard deviation over square root of n, and that becomes the margin of error plus or minus X bar. Otherwise, it's pretty much the same as the confidence interval for Z-scores. Interpretation and everything else, exactly the same. And with that, I'm going to go ahead and wrap up this video, and I'll see you all next time.